and you haven't, I think there's actually, I apologize that we had 3, but apparently there was 3 different release forms for your presentation. Anytime you've got a host organization and then APL hosts the website and you get a bunch of lawyers involved, there's no end of forms they can come up with to get approval. So if you're a presenter and you haven't filled out all 3 of the release forms, please see the registration desk and we can get that done. That way we can get these presentations uploaded because as you've seen, we're having a little bit of trouble with our streaming service, and so at least if we can get the presentations uploaded so that our remote attendees can get access to those. So again, if you're a presenter, you haven't filled out 3 release forms, please see the registration desk. With that, we have 2 presentations left, and then we'll have another couple of giveaways before we wrap up the day. So our next presenter is Eileen Liu. Did I get that right?
Yes, you did.
And anyway, so take it away.
Thank you. Hi, everyone. My name is Eileen Liu, and I'm on the Lockheed Martin Next Step team. So I'm based out of the Waterton campus in Colorado, and we're currently finishing up on the Next Step Phase 2 study contract. So just to give you a little context, since you've been hearing that contract a lot, you've been hearing Next Step, you've been hearing Lunar Orbiting Platform Gateway a lot, I'll just give you a little context of what we're trying to do. So in this study, we're really just trying to inform NASA and do some research on different design concepts for the Gateway. The Gateway is meant to be a space station in lunar orbit, so that's why the moon is so large in this picture here. So it's meant to be a manned mission where you can have up to 4 astronauts in there. So I'll just kind of break down what those different components in this picture are. So you can see Orion right here. This is what would be bringing all the astronauts and the crew up to the Gateway. You have the habitat module over there. This is where the crew would be doing a lot of their science experiments, where they'd be doing a lot of their living, working, eating, etc. You have an EVA module, you have a utility module, and then really importantly, you have a power and propulsion element here. And so a lot of the work that we've been doing is looking at all these different components, looking at how we can just maximize all of our heritage software and hardware, and also trying to bring in a lot of the NASA investment with CFS, for example, all the tools that they've been working on to develop an integrated modular low-cost system. So for today, I'll first be giving you a little context of just our heritage software at Lockheed Martin, all the years of experience that we've had. Then I'll move into some more of the details of the study contract itself, talking about some of the insight that we've gained about CFS and how to integrate it with high heritage software, some of our key takeaways, and just how it all wraps into the Lunar Orbiting Platform Gateway. So Lockheed Martin, we've had over 40 years of planetary spacecraft experience. So on the right, you can see this timeline here. So we date all the way back to Viking in 1975 in the bottom right over there. And so you can see this is going through a variety of different spacecraft leading all the way up to Lucy in 2021 for estimation right now. So all these years of experience includes hardware, software, integration, test, and more. And through all these decades, we've had diverse sets of mission requirements for all the different planets we've been going to and just what we're trying to do with each of the spacecraft. We've had incremental hardware evolution with increasing advances with rad hard and reliable hardware. That's led us to be able to consistently evolve our flight software and our baseline. Through all these years, we've also gained really strong operations focus. So we have the mission support area under our Denver office. So there we've learned a lot about how to have shared resources, shared people, and how to operate all these different spacecraft at the same time. And with all these different spacecraft, we've also had to interface with different NASA interfaces. It's okay. So all this has been possible because of our product line focused organization. So with our product line organization, what we're really trying to do is minimize specific functionality for each spacecraft. We're trying to think ahead to the next spacecraft. And so we design our software in a way where we try to make everything very portable, very modular, and just make it so it's not specific to the one spacecraft that we're designing on at the time. And so we've been able to do that. In doing that, we do buy down risk, we buy down cost, we buy down schedule for our future spacecraft just because we're using proven hardware and software through the years, and it's consistently adding to our baseline. So in our baseline, we've combined our commercial and civil space organizations. So we've taken the best of both worlds, taken all the best lessons learned from those both different businesses. And this has really driven commonality between these businesses and helped us develop a strong baseline. that leverages the strengths of both. In addition to all that, in our software organization, we've been trying to build up our CFS expertise. So earlier you heard presentations where we've been using CFS in Orion, for example, and backup flight software and our camera control. We've been doing qualification at Lockheed Martin with our research and development, our investment into CFS. We've been building our own CFS applications. In addition to all this, we've been working on integrating CFS with our Common Core, just seeing how we can use all the good work and the tools that NASA has been developing. So in the bottom right, you can just kind of see a little bit of a snapshot of some of our portfolio. So you can see that it covers all these different areas. So it covers various orbits, different power and bus sizes and missions. And this is all enabled just through our product line focus. So at Lockheed Martin, we're integrating our planetary flight software and CFS components. NASA has done a lot of investment into integrating the CFS bus network, which I'll be talking about in a couple slides, and SBN Lib as well, which Robert Hirsch talked about earlier. SBN Lib really provides an architecture-agnostic interface to CFS, which enables us to quickly have interoperability with our flight software product line. And with all the investment that NASA's been doing in looking into time-triggered Ethernet, for example, our voting architecture, it also makes it really easy for us to leverage all of NASA's investments with our baseline as well. A big part of the reason why there's also a lot of easy integration between our product line and CFS is because they have a lot of shared design principles. For example, both are modular and layered architectures. They both maximize leverage from heritage spacecraft. Again, where I was talking about the reusability, we try to reuse proven hardware and software to buy down the cost, schedule, and risk. We minimize clone and own, which is where you just take all the software and hardware from an existing spacecraft, claim it as your own, change it to your specific needs for your mission, and then just calling it your own and not really thinking about future spacecraft. So by having that modular approach, we're thinking ahead for future spacecraft and trying to compartmentalize all this different functionality. You can really minimize the clone and own, and you can continue to build upon your baseline. So these commonalities have helped provide a unique opportunity to leverage the best of both worlds. So you can see this table in the bottom, just some of the key features for CFS and LM1000, our baseline, for example, and just all the benefits of both. So earlier I touched upon the Next Step Phase 2 study contract. So there are a variety of different study topics that we were asked to look into. I've highlighted two of the study objectives just for the purposes of our discussion today. These will be assessing multiple architectures to optimize safety, affordability, and performance for the gateway. And another one was to demonstrate crew interface commonality between gateway assets and NASA's Orion. So a big part of how we looked into these two objectives was by taking the action to gain experience with integrating sample payloads to inform our architecture design decisions. So a lot of these applications up here, they aren't anything new. A lot of them have been discussed this morning already, but for those on the line who didn't necessarily hear those presentations, I'll just give a really quick overview. So in the top right, you can see the key layers of CFS. So at the bottom, you have the platform-specific package, which is the layer that's abstracting away all the hardware-specific needs. You have the OCell, the operating system abstraction layer, which is abstracting away OS needs. And then above both of these layers, the framework, as they called it, you have the CFE, the Core Flight Executive Services API. And then you also have the mission-specific and the reusable CFS applications. So for our discussion, I'll be focusing mostly on the CFE and the CFS layers. So in the bottom right, you can see everything is color-coded. So the really key application that we've been looking into has been the software bus. So this is a CFE application. It enables inter-application messaging within a CFS implementation. So if you have different applications, this is your means for these different CFS applications to talk to each other. It uses a pub-sub messaging pattern with unique message IDs. And so SBN, which is the software bus network, is then a CFS application that builds upon the SB capabilities. It extends the software bus messaging service across partitions, processes, and networks. It allows applications within different CFS peers to send messages to each other. And this is because sometimes you don't have all the applications co-located on the same platform, or just in general, you want to have different peers within networks to be able to talk to each other. Building upon the SBN, we have the SBN Lib, the Software Bus Network Library. And so this is a standalone interface library built from that. It builds upon the SBN application. And so it allows for non-CFS compliant peers to communicate with CFS compliant peers. And so it does this because it's just built into shared object library that you can then just include with any project. So again, it's architecture agnostic, so it's really easy to ramp up and do some prototyping with SBN Lib. And so some of the key things from these three applications is to note that SBN can communicate with other SBNs or SBN Libs, that the software bus itself, it can only communicate with SBN. And so if you want to talk to another peer, you wouldn't be able to have the SBs talk to each other directly. You'd have to have an SBN application. So the bottom right diagram just reiterates that the SBN library builds upon the SBN, which builds upon the capabilities of the software bus itself. So all that said, there are a few different options for how you use these different tools for integrating different payloads into something like the gateway. So the first option would be the ideal option, where you can enforce full CFS implementation for all peers. So in this way, you have a fully cohesive platform because you would know that you would have all the different layers included in all these different peers. However, this would add complexity for your payload design. So a lot of times payloads are designed by scientists from PhDs who aren't necessarily software focused. And so when they first started designing their payload, they might not have been thinking about, oh, I need to include a full CFS instantiation. And so when they are designing how they send in their commands, how they send out telemetry, it might not be so focused towards CFS. And so it just adds extra time and cost. And so depending on what you're trying to do, that can just be added complexity, added time and money that you didn't anticipate for. Option two is where you use almost like a control node, where you have one node that's fully CFS and then where you have other peers that are mostly just using SBN library, the shared object library. So this would be easier to integrate after a payload had been fully designed, because again, it's just a shared object library that you'd include within your project. It allows for flexibility with configurations. However, you'd overall have a disjointed platform just because you can't use other services within the CFE layer, for example. A really big downside too is since SBN Lib, it does need to have at least one instance of the software bus running. If you ever had an issue with that one peer that has the software bus running, if it ever went down, then your whole network would go down, and then you wouldn't be able to communicate across your peers anymore. So third option is then more of a hybrid approach, where you have some peers that are using the full CFS instantiation, and then some of the peers where they're just using SBN Lib. So this would allow for the greatest modularity. However, it would become an issue because then where would you draw the line where you enforce CFS fully for some partners who are integrating for a full system, and then where you say, oh, some people, you're just okay to use SBN Lib. So where would you draw the line in terms of saying you can use SBN Lib versus the full CFS instantiation? And so in this way, it would be more ideal to then just say, okay, everyone has to be fully CFS compliant. But this can pose a problem just if you're so far along in design where you hadn't really anticipated that up front, where somebody might already be building up a full platform that didn't anticipate CFS at all, and just, again, adding time and complexity to your solution. So some of our key takeaways in doing all this research came down to these main four, including others, but I'll talk about these four for now. So SBN Lib itself, it's a really great tool. It allows for quick prototyping, so it's good for you to be able to first check with your payload or some end system to see how it will communicate with all the other peers in your network. However, as I said before, it does need a full software bus running on some peer. So even if we did decide to really mainly focus on and depend on SBN Lib, we would still need a sort of control node. So the control node would make it easier to update tables, schedules, and configurations. However, it would become a critical component, and as I said, if it ever went down, then your whole system would come down. Another big thing that we found was that SBN connections currently do have to be defined at start time. So that is great if you do know all your payloads and all your peers up front. However, if you're in something like the gateway, for example, where you might have to bring up other payloads in the future, since the gateway has a 15-year design life, that could pose an issue because each time you brought up a new payload, you'd have to temporarily pause all your different end systems. You'd have to update all their different tables and then bring up the system again. So you'd have to have a system restart. So I know this is something that NASA's been working on, but the time being right now, they're all defined at start time. Another limitation is that the software bus currently limits the total number of message IDs to 256. And so depending on how many commands and telemetry that you have for each peer, that could limit the total number of peers that you have on your network. So for many cases, this would be okay, but if you keep on wanting to build up a more and more cohesive platform, or you're switching out different payloads, this could pose to be an issue later on down the road. And so before I wrap up for today, I just want to reiterate that all these different findings and research that we've been working on, this has really been to help us inform NASA and ourselves just how to build up a cohesive gateway. We have to anticipate the scalability, because with that 15-year design life, you don't know what payloads might come up down the road, and so you have to anticipate and be able to be ready to take in all those different payloads. And so with the modularity of both CFS and our high heritage software, we're enabled to really be able to anticipate and adapt to new payloads that might come up. We're able to partner with international partners. And in addition, we can build up a fully integrated modular system with standardized interfaces. Thank you. Does anybody have any questions?
Actually, yeah, sorry, actually, I have notes, so let me, all right, I got it. On your SBN, or at least your instantiation of SBN and SBN Live, are you serializing the data?
So with SBN Live, yeah, so fully going with the CCSCS format, yeah.
Okay, so but I mean, it's not serialized, it's just in the binary format then?
Yes, yeah.
Okay, is it internode? Is it on the same CPU, or is it going from one CPU to another?
It could be on separate CPUs.
Okay.
Yep.
Thanks.
I just had a comment rather than a question on the limitation of the software bus. I think if you move to the extended header for CCSDS, you can have more nodes. So we experimented with that successfully, I think, last year, and can see that works. So
okay,
at least that, I think if folks are still in the early stages, it might be good just to buy into that. So it's already built in to development with multiple nodes.
Just a quick comment. The original SBN, and I thought it was still in the current one, is very dynamic, that you could send a command to say accept new nodes and update the table, and then new things can come and go and join very dynamically. So it was originally put in there so it just wouldn't accept any new node because it was a security issue. You just can't have new things appearing in space out of nowhere.
Right.
So
Gotcha.
you had to configure it, but you shouldn't have had to restart it.
Okay. I think that's more of if in the beginning, if you defined all the extra slots, and that'd be okay.
He owns it now, so it's just
Gotcha.
I'm a government employee. I don't know anything. SBN, you have to actually at load time, when the app loads, it loads a text-based table. Well, actually, it's now a table-based table. But it's at load time. It's not. But you can predefine 1,000 nodes and only have 10 up at a time, and it dynamically manages connections and all that. So, and actually, it's how DTN might play into that space, I think, is still a big question mark too. And I know we've all talked about DTN at various points, so that may also help alleviate the dynamic nature of this the gateway vehicle.
Mm-hmm. Thanks, Chris.
Any other questions? Okay, thank you.
Eileen.